Welcome to Mrs. Neller's notes for her double block algebra class. These are the notes for section 12.2 entitled Operations with Radical Expressions. And today we're going to talk about how we can add, subtract, multiply, and divide radical expressions. And we just reviewed section 9.3, which talks about how we're going to break down radicals. So we're still going to use some of that today. And remember that when we're simplifying radicals, you have to take out the biggest perfect square. So that means we're going to divide any radical that's not already a perfect square by the biggest perfect square that goes into it. And those perfect squares are 4, 9, 16, 25, 36, 49, oops, 36, 49. And again, I'm getting these by just doing 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7. So then we have 8 times 8, 9 times 9, 10 times 10 is 100, 11 times 11, 12 times 12, 13 times 13, and then 14 times 14, and then 15 times 15. And those are the list of perfect squares that we've been using since chapter 9. So anytime we have a non-perfect square, like the square root of 50, that non-perfect square that's inside the radical, then we want to find the biggest perfect square that goes into it so we can break it down. And the biggest perfect square that goes into 50 is going to be 25, and it goes in there 2 times. So then we can take the square root of 25 because that's a perfect square now, and then we have our little radical left over. So we're still going to be using that skill today. And then we are also, since we're adding and subtracting and multiplying and dividing radicals, when we add and subtract, we have to have like terms. Okay, so that's just when we're adding or subtracting. And like terms with radicals means that they're going to have the same radical. So like 3 square root 5 and negative 12 square root 5. Those are like terms because they have the same radical, square root 5 and a square root 5. So then we could add or subtract them together. But if we had something like 2 square root 7 and then again negative 12 square root 5, those aren't like terms because this one has a square root of 7 and this one has a square root of 5. So those are not like terms. So here for our first example, we're going to be putting that knowledge of like terms together. So we're going to take our expressions and we're going to simplify them first. So we might have to break them down. And then we'll see if we can combine any of our like terms together. Now for our first example here, we have the 4 times the square root of 5 and 2 square root of 5, and they're being added together. Now the square root of 5s, those are already as simplified as they can get. There aren't any perfect squares that will divide into them evenly, and they're both the same. They're both square root 5 and square root 5. So these are going to be like terms. And when that happens, then we can look at the numbers in front, the 4 and the positive 2. Actually, let me circle the 4 and the plus with the 2. We want to take the sign with the number. So we can do that 4 plus 2 and get 6. So now we have 6 square root 5s. So it's kind of like taking 4x plus 2x and getting 6x. Same concept. And you can do that as long as the radicals are the same, as long as they have the same radicand inside. Okay, now for part B, I have 8 times the square root of 28 minus 2 times the square root of 3. Now the square root of 3 is already as broken down as it'll go. I can't reduce that anymore. But the 28, it's not a perfect square, but I can reduce it. I can break it down by dividing by a perfect square. And the biggest perfect square that goes into it is 4. The square root of 4 times the square root of 7, because 4 times 7 is 28, and 4 is a perfect square. Remember, when you're breaking down a non-perfect square, you have to use a perfect square. So one of your numbers has to be a perfect square. So then the square root of 4 is 2, and then the square root of 7 is my leftovers. Now I still have this 8 in front that's being multiplied by the whole thing. So 8 times 2 is 16. So now I have 16 square root 7, and then I'm going to bring down the rest of this expression here. Minus 2 times the square root of 3. And now I have the square root of 7 and the square root of 3. However, those aren't like terms because they don't have the same radical. So I can't actually do anything more to this expression. I'm just going to leave it. So I was only able to break down the square root of 28 and simplify 8 times the square root of 8 into 16 square root 7. That's all I was able to do. Now, ideally, we want to be able to break down our radicals and combine them with other like terms. So let's see if that happens this time in example C. I've got the square root of 72 minus the square root of 18 plus the square root of 50. None of those are perfect squares, so I'm going to see if I can break each of them down. Now 72 I can break down into 36 and 2. So that's going to be the square root of 36 and the square root of 2. And the square root of 36 is 6. And then 18, I can break that down into 9 and 2. The square root of 9 and the square root of 2. The square root of 9 is 3. So I'm going to bring down this subtraction. So minus 3 square root 2. Now, lucky here, I've got square root 2 and square root 2. So eventually I'll be able to combine those terms together. And then for 50, oh, that's the example I did up above. We can break this down with the square root of 25 and the square root of 2. And the square root of 25 is 5. So now all of my terms have the square root 2 in them. So here I have 3 like terms. So now I'll be able to add or subtract those coefficients in the front. So the 6 and the negative 3 and the plus 5. That's what I'm going to be adding and subtracting together. So 6 minus 3 is 3, plus 5 is 8. So I really get 8 square root 2's. That's how many square root 2's I have altogether. And that's ideally what we want to happen. We want to be able to break down our non-perfect squares, so that way we have like radicals, and then we can combine our like terms together. Now, in this next example here, this is just a refresher of some multiplication skills that, again, we've been talking about since chapter 9. And remember, when you have two radicals that are being multiplied together, you can multiply the numbers inside of them and get one big radical. And if there's any numbers out in front, any of the coefficients, you can multiply them together. So we say we can multiply a number by a number and a radical by a radical, but you can't multiply a number by a radical. You can't multiply them together. You just write 5 square root 7, okay? You would just leave those together. That is not equal to the square root of 35. Okay? So we can multiply a number by a number and a square root by a square root. So in part A here, we have a square root times a square root. We have the square root of 8 times the square root of 18. So I'm going to multiply 8 and 18 together. So 8 times 18 is 144. So now I have one big square root. It's the square root of 144. Now that's a perfect square, and the square root of that is 12. And that's what we want to happen every single time, if at all possible. We want to be able to multiply our radicals together, get a big radical that's a perfect square, and then we can take the square root of it. But that doesn't always happen. So here in this next example, I have the square root of 6 and the square root of 10. Again, they're both radicals, so I can multiply the 6 by the 10 and get 60. So now I have the square root of 60. That's not a perfect square, but I can break it down. 4 is the biggest perfect square that goes into it. And the square root of 4 is 2. So I can simplify it back down into 2 square root 15. And again, this is the same skill that we saw in chapter 9. So this is a review here. Now part C is going to take this and kind of step it up a notch, because here we're actually distributing. So this is new. This is a new type of multiplication here. But these rules still apply, where it's a number times a number or a square root times a square root. So here I'm going to distribute the square root of 3 to the 5 and to the square root 7. So if you want to write it out, you can. I'm going to have the square root of 3 times 5 plus the square root of 3 times the square root of 7. Now writing the steps out is going to help you see that here in this first part I have a number times a square root. I can't do that. I can't multiply them together and get 15. So I just have to write it as 5 square root 3. We always want to write the whole number first and then the radical. But now for the second part, I have the square root of 3 and the square root of 7. Those are two radicals, and I can multiply them together and get the square root of 21. Now I can't break down 21. It's not a perfect square, but I can't break it down. There aren't any other perfect squares that go into it. And it's not a like term with the square root 3, so I can't combine my coefficients in the front. So actually, that's all I can do for this problem. So this type of problem here, where we see the distribution, this is a newer concept. Not that distribution is a new concept, but distributing with a radical, that's a new concept. So just remember that you can multiply a number by a number and a square root by a square root. But when you have a number times a square root, you just have to write them next to each other. All right, now for example 3, we're going to use this same skill. We're still going to be distributing, except this is where we have our special patterns for multiplication, and they call them the sum and difference pattern. And that's because one term has a subtraction and one term has an addition. Otherwise, they're exactly the same. So I have the square root of 3 and a 5, and the square root of 3 and a 5. Square root of 7 and a 2, square root 7 and a 2. But there's a plus and a minus, or a minus and a plus. Doesn't matter what order the addition or subtraction is in. But when we do our distribution here, there's a special name for it, and it's called foiling. That means we do first, outer, inner, last. The first terms, outer terms, inner terms, and then last terms. That's the order that we multiply them together. But really, it's just doing a double. Oh, what's going on with the... Okay, so we've got our foiling, but really this is just a double distribution. Oh my goodness. Okay, don't know why it keeps doing that. Okay, so it's just a double distribution. That's really what we're going to be doing here. So I'm going to take this square root of 3, and I'm going to multiply it by the other square root 3 and the 5. So again, if you want to write them out, you can. We've got the square root of 3 times the square root of 3, and then I'm going to add here, and I'll have the square root of 3 times the 5. Now I'm going to switch colors here so I can see my next step. Now I'm going to take my other term in the first set of parentheses here, this negative 5, and I'm going to multiply it by the square root of 3 and the 5. So now I'll have minus 5 times the square root of 3, and then minus 5 times a positive 5. So you can see that when I drew in those little rainbows, I did my first terms, the square root of 3 times the square root of 3, then my outer terms, the square root of 3 and the 5, then my inner terms, the negative 5 and the square root 3, and then the last terms, the negative 5 and the positive 5. So that's what the FOIL means, first, outer, inner, last. It's just following that rainbow pattern when you draw in those rainbows and do your double distribution. Okay? So now we have to actually multiply and simplify our expression here. The square root of 3 times the square root of 3, that's the square root of 9, which is really just 3. And then here I have a number times the square root, which I can't do. So I'll just write 5 times the square root of 3. Remember, we want the number to be in the front. Same thing here. I can't multiply the 5 and the square root of 3, so I'll just write them together. But then the number times the number, I can do that, minus 25. Okay, so now that I've actually done the multiplication, I want to look for like terms that I can combine together. And here I have a square root 3 and a square root 3, so I can combine them together. One's a positive 5 and one's a negative 5. Remember, we're adding those coefficients out front. And positive 5 and negative 5, when I add them together, I get 0. So those middle terms with the radicals end up canceling. And that's because I have a sum and difference pattern. I have one term with a plus and one term with a minus. So now all I really have to do is 3 minus 25, which is a negative 22. So let's take a look at part B here. And hopefully this will go a little bit faster now that we've seen all the steps in part A. So I'm going to take my first terms and multiply them together. Square root of 7 times the square root of 7. And then my outers, so negative 2 times the square root of 7. Then my inners, the positive 2 times the square root of 7. And then my lasts, the 2 times the negative 2. So here I have a radical times a radical, which I can do. 7 times 7 is 49, and the square root of 49 is 7. And then here I'll have 2 times the square root of 7. I can't multiply them together, so I just write them next to each other. And then I also have plus 2 square root 7. And then 2 times negative 2, I can do that. That's a number times a number. Now again, my middle terms have radicals that are exactly the same, but the coefficients in the front are a 2 and a negative 2, so they end up canceling. And then I end up doing 7 minus 4, which is 3. Okay, so the double distribution shouldn't be too intimidating. That should be pretty nice and easy to do. And if you have one term that's a positive and one term that's a negative, those middle terms are going to cancel. Now, we can still do this where you don't have opposite signs and you don't have all the terms that match, and then the middle terms won't cancel as often. So there are different variations of this that we can do, but this is what you're going to see in your homework tonight. And why we want to practice that concept is for this last example here. When we're dealing with fractions and radicals, remember you cannot have a radical in the denominator. That's not allowed. So in order to do that, you have to either multiply by that radical that's in the denominator, if you just have a radical, or if you have a binomial, you have to do a process that's called multiplying by the conjugate. And the conjugate is just where you change the sign. So if I have 3 minus the square root of 2, then my conjugate for that is going to be 3 plus the square root of 2. So the terms stay the same, you just change the sign in between. And that is so that we will get terms that cancel out the radical. So if this was my original term, then this 7 minus the square root of 2, that's my conjugate. And when I do my double distribution, then those radical terms go away, and I just get a whole number for my answer. So we're going to be doing that process in the denominator, so that way I get the radical out of the denominator. Now, example A and B here are just review. We've seen problems like this back in chapter 9. And here in example A, you have 4 divided by the square root of 3. And that's an okay term, except we can't have that radical in the denominator. So to get that out of there, I'm going to multiply it by itself. I'm going to multiply by the square root of 3. And what I do to the bottom, I have to do to the top. And I want to do that because in my numerator now, I have 4 times the square root of 3, which I can't multiply together, so I'll just write 4 times the square root of 3. And then in my denominator here, I have the square root of 3 times the square root of 3, and I can multiply a radical by a radical, so I really get the square root of 9, which is really 3. So now in my denominator, I don't have a radical anymore. I have a radical in the numerator, but that's okay. The numerator likes every single possible term. Positives, negatives, radicals, non-radicals, that's okay. The denominator is very exclusive. It doesn't like any radicals. Now, the only other thing we could do to this problem is if the 4 and 3 were able to be canceled, we could do that. We could simplify those terms down, just like it was a regular old fraction without a radical. So if we had 4 over 8, then we could reduce that to 1/2. But I can't reduce 4 over 3, so we'll just leave it. So now for part B, I have a radical in the numerator and the denominator. That one in the numerator, that's okay. This one in the denominator, that's a problem. So I'm going to multiply it by itself so that I get it out of the denominator. And then now in the numerator, I have a radical times a radical, which I can do. So I get the square root of 21. I get a bigger radical. And then in my denominator, I'll have the square root of 7 times the square root of 7, which is the square root of 49. But the square root of 49 is a perfect square. That's 7. Now the 21, it's not a perfect square, and I can't break it down. So I'll just leave it the square root of 21. Now there's nothing else that I can do to this problem to simplify it. Sometimes students see the 21 over the 7 and they think, oh, 7 goes into 21 3 times. But it's actually not 21, it's the square root of 21. So any number that's inside that radical can't just be divided by a whole number in the denominator. So we're done with that problem as well. We can't reduce it anymore. And again, those are two problems that we saw in Chapter 9. So if you didn't master it back then, here's your chance to really get a good grasp of it now. Okay, these last two examples, this is where we're going to be doing multiplying by the conjugate. So let me write that up here. We're going to multiply by the conjugate. And you hear conjugate a lot when you're dealing with other languages like Spanish or French. You're going to conjugate your verbs. This is a slightly different meaning, okay? And remember, like I said before, the conjugate is going to be the same binomial that has the radical in it, except you're going to change the sign. So here for part C, I have 6 in the numerator, which is fine, but in my denominator I have 6 plus the square root of 3, and that radical in the denominator is a problem. And the only way I can get rid of it when it's being added to a whole number is if I multiply by the conjugate. And again, what I do to the denominator, I have to do to the numerator. Square root 3, there we go. So 6 minus square root 3. That's what I'm going to multiply the numerator and the denominator by. Now in the numerator, I'm going to be doing just a single distribution. In the denominator here, I'm going to have a binomial times a binomial. So I'm going to be doing what I did in example 3. Okay, so in my numerator now, I'll take the 6 times the 6, and then the 6 times the square root of 3. So 6 times 6 will be 36. And then 6 times the square root of 3, I can't do that, so I'll just write minus 6 square root 3. Now in the denominator, I'm going to do that double distribution. So I'm going to take the 6 times the 6, and then the 6 times the negative square root 3. So 6 times 6 is 36, and then I'm going to have minus 6 square root 3. So it just happens to look similar to my first terms in my numerator here, but that's just coincidence for now. And then in the denominator, I'm going to do the other part of my distribution here, the square root of 3 times the 6, and the square root of 3 times the negative square root 3. So then I'll get a positive 6 square root 3, and then a minus 3, because the square root of 3 times the square root of 3 is the square root of 9, which is a perfect square, that's 3. Now, again, the whole reason we do that is so that when I combine my like terms in the denominator, I have a negative 6 square root 3 and a 6 square root 3. They'll cancel. And then I just have to do the 36 minus the 3. So now, when I combine those like terms in the denominator, I have 33. My radical has completely gone away. And then I still have 36 minus 6 square root 3 in my numerator. I can't combine those together because they're not like terms. But if I look at all of my whole numbers, my coefficients, I have a 36 and a 6 and a 33. All of those numbers can be reduced by 3. So I'm going to reduce them just like they were fractions. So if I divide all of them by 3, I'll have 12 minus 2, and then little leftover square root 3, over 11. Remember, you cannot reduce the square root of 3 because he's inside that radical sign. Okay, so let's practice that one more time so we can see those steps again. Now again, in part D here, I've got 9 in the numerator, which is fine, but in the denominator, I have 5 minus the square root of 7, and that square root 7 is the problem. And I can't just multiply by the square root of 7, because then that just gives me a square root of 7 with the 5. So I have to multiply by my conjugate, 5 plus the square root of 7. That way when I do my distribution, those middle terms with the radicals will end up canceling. So again, in my numerator, I'm going to do a single distribution, and in my denominator, I'm going to do that double distribution. So in my numerator, I'll take 9 times 5, and then 9 times the square root of 7. So 9 times 5 is 45, and then 9 times the square root of 7. I can't multiply a number by a radical, so it's just 9 square root 7. Then in the denominator, I'll do 5 times 5, and then 5 times the square root of 7. So 5 times 5 is 25. Those are two numbers that I can multiply together. And 5 times the square root of 7, that's a number and a radical, so I'll just leave it, 5 square root 7. And then the other part of my distribution in the denominator is to do the negative square root 7 times the 5, and then the negative square root 7 times the square root 7. So I'll have minus 5 square root 7, because again, I want to write that whole number in front. And then square root 7 times square root 7 is the square root of 49, which is 7. So that'll be minus 7. So now again, in my denominator, if I look at my like terms to combine together, I've got a 5 square root 7 and a minus 5 square root 7. They'll eliminate. They'll cancel. That's what gets rid of my radical in the denominator. And then I just need to do the 25 minus 7, which is 18. And then in my numerator, I have 45 plus 9 square root 7. And let's see, let's take a look at those numbers. The 45 and the 9 and the 18. Not the square root of 7 because he's inside the radical sign, so we're just going to ignore him for now. But the 45 and the 9 and the 18, they can all be divided by 9 to reduce them. So I'm going to end up with 5 plus 1 square root 7 over 2. And you don't have to have the 1 in front of the square root 7. If you just wanted to write 5 plus square root 7 over 2, that's okay. But the 1 I just put in there to show that we divided the 9 by the 9. And that's just like how in this previous example here, we took the 3 and 36 and the 6 and the 33, and we divided them all by 3. But again, you can only do that to the numbers that are out front of the radical or the numbers that are just constants by themselves. So it's either the coefficient or the constant, not the number that's inside the radical. So those last couple examples, those are the toughest because it's combining lots of steps together. But that process of multiplying by the conjugate, it's important. It doesn't go away. You'll see it in geometry, you'll see it in algebra 2, trig, pre-calc. It's a very useful, very common math concept. So definitely practice these problems. Some of them are odd, so you can look them up in the back of the book. But if you have questions on any of them, come and see me before school.